In this video I will be looking at Unit 2 Various Chemistry for the Edexcel exam board, and in particular I will be covering kinetics and chemical equilibria. Chemical kinetics is the study of speed or the rate of a chemical reaction. It is important for many industrial processes because of economic reasons. It's also useful in medicine. It allows us to determine how quickly a particular medicine will work in the body. For a reaction to happen, we need three things. First, we need a collision between the reacting particles. Two, the reacting particles must have sufficient energy to break their existing bonds so that new bonds can form. This is known as activation energy. And the particle must collide in the correct orientation. As we can see from this picture, when these particles collide, is an effective collision. In this case, because the orientation is not in the correct way, the particles simply bounce off each other. Factors that affect rates of reactions are concentration, pressure, temperature, surface area, and catalysts. Let's first talk about the concentration. If we increase the concentration, it increases the rate of the reaction because there is an increase in the frequency of the collisions happening between the particles. If we increase the pressure, this will lead also to an increased rate of the reaction. This only applies to gases. When we increase the temperature, there is an increase in the collision frequency of the particles because the particles now have more kinetic energy. If we increase the surface area of a solid, this also increases the rate of the reaction. And catalysts increase the rate without being used up themselves. When we increase the temperature, we increase the kinetic energy of particles. At a given temperature, the particles have a range of energies and not just one specific energy. With increased temperature, we increase the distribution of molecular energies, and this can be represented by a Maxwell-Boltzmann distribution as shown here. On the x-axis we have the kinetic energy, and on the y we have the number of molecules. We also have two curves. The red one represents a high temperature and the blue one represents a low temperature. Some important things we need to note about this diagram. First of all, is that no molecules have zero energy. Each curve rises to a peak and back down without actually touching the x-axis. The higher temperature peak moves to the right and slightly lower than the lower temperature. The area under the graph is the same for both the blue and the red line because we have the same number of particles. We also have here this line representing the activation energy, and the activation energy is the minimum kinetic energy that colliding molecules must have for the collision to be successful and for it to result in the formation of the product. The red area under the curve, which is to the right of the activation energy, shows us the fraction of molecules that have the necessary kinetic energy to react upon collision. Let's look at the role of catalysts. A catalyst provides an alternative route for a reaction which has a lower activation energy. So it speeds up a chemical reaction without undergoing a permanent chemical change itself. Catalysts are very useful because they give us better atom economy, which means that less waste is produced in a chemical reaction. Here again we have a Maxwell-Boltzmann distribution. We have the number of particles on this axis and the energy on this. We have also the original activation energy as shown here, and the new activation energy is shown here with the use of a catalyst. So the tinted area under the curve to the right of each activation energy shows us the fraction of the molecules that have the sufficient energy to react. So we can see originally we only had the green area. So this represents the number of particles that had sufficient energy to react before we added a catalyst. When we add a catalyst, we can see that the area increases, meaning that we now have a larger fraction of the molecules that have a sufficient energy to react. We can also use a reaction profile diagram, and this shows us the energy levels of reactants and products and also the transition state. We can see we are starting off with the reactants here, and the products are lower down because we have an exothermic reaction in this case. We have two activation energies. The blue arrow represents the activation energy without a catalyst, so we can see the barrier is a lot higher than the barrier as represented by the red arrow, which is the activation energy with the catalyst. So this clearly shows us that if we have a catalyst in this particular example, it provides an alternative route which has a lower activation energy. Catalysts can be divided into two broad categories, into homogeneous and heterogeneous. Homogeneous catalysts are in the same phase as the reactant. Here I have an example of a homogeneous catalyst and how it works. We have persulfate ions, which are a very powerful oxidizing agent, which oxidizes iodide ions into iodine. This reaction is shown here between the solutions happens very slowly, and this is because the reaction needs a collision between two negative ions, this one and this one. There is a lot of repulsion between these two, which is an obstacle. To overcome this obstacle, we can use a catalyst, iron 2 plus. If we add the iron into the solution, the persulfate ions will oxidize the iron 2 ions to iron 3 ions, as shown here. In the process, the persulfate ions are reduced to sulfate ions. This is the intermediate stage. The iron 3, which was produced here, strong enough so they can act as oxidizing agents and oxidize iodide ions to iodine. In this process, they are reduced back to iron 2 ions, which shows us that iron 2 ions in this case are the catalyst because they are not used up in the reaction and they are regenerated in the end. We also need to know how to carry out an experiment with the decomposition of hydrogen peroxide. This is the equation of the decomposition of hydrogen peroxide. We can see we're starting off with aqueous hydrogen peroxide and producing water and oxygen gas. This reaction is very slow without a catalyst. An appropriate catalyst in this case could be bromide ions, where we can see when we add the bromide ions into the hydrogen peroxide under acidic conditions, we have the formation of bromine and water, and bromine and the formation of water is the intermediate step. Bromine that was produced in this step then reacts with the hydrogen peroxide to produce oxygen gas, and the bromide ions are regenerated. On the right here we can see red line. This is the decomposition of hydrogen peroxide without the use of a catalyst. It is much higher than the blue line, which represents the catalyzed reaction where we're using bromide ions. The other type of catalyst is known as heterogeneous catalysts, and these are in a different phase from the reactants. One example of the use of heterogeneous catalysts is the Haber process, where the catalyst promotes a reaction through the active site, and the active sites are found on the surface of the catalyst to which the reactants can bind. This is the general equation for the Haber process, which is the synthesis of ammonia from nitrogen and hydrogen gases with the use of a metal catalyst. So we start off with the gaseous reactants and the active site of the catalyst, which produces the adsorbed reactants. The adsorbed reactants then become adsorbed products on the surface. Adsorbed products then are released, which means that we now have gaseous products and again free active sites. So this reaction can happen again. The important thing to remember here is that there are fewer active sites than reactant molecules. So if we increase the pressure, there will be no effect on the rate of the reaction because active sites are already occupied. Another example is the use of platinum as a catalyst when adding hydrogen to alkenes to produce alkanes. In this diagram we can see the purple balls represent the platinum. We have hydrogen and carbon being adsorbed to the metal surface. When the hydrogen-hydrogen bond breaks, hydrogen atoms migrate along the metal surface, and then ethane desorbs from the metal surface. We also need to talk about chemical equilibria. Chemical equilibria is only possible in a closed system. The three main things that we need to know are that reactions that do not go to completion, where the end of the reaction has both products and reactants, reactions that are reversible, meaning that the products can be converted back into reactants and vice versa. And the term dynamic equilibrium refers to the rate of the forward reaction is equal to the rate of the backward reaction, and there is no further change in the concentration of both the reactants and the products. In this diagram, we can see on the x-axis we have time and rate on the y-axis. This line represents the forward process and this is the reverse process. And here is where the equilibrium is reached, which means that the rates of both the forward and the reverse happen at the same rate. And please remember that reactions do not stop once they're at equilibrium. It just means that there is no further change in the concentration of both the reactants and the products. We need to know about Le Chatelier's principle, which states that when the conditions of a system that is in equilibrium are altered, the position of the equilibrium will alter in such a way as to try and restore the original conditions. It will try to oppose the change. In this example here, we have N2O4, which is a yellow gas. Nitrogen dioxide is produced, which is a brown gas. If the position of the equilibrium shifts to the right, the flask will turn reddish-brown as shown here, because there is an increase in the production of nitrogen dioxide. If the position of the equilibrium shifts to the left, the flask will turn pale yellow as shown here, due to the increase in the production of N2O4 gas. If a system at equilibrium is disturbed either by a change in concentration, pressure or temperature, the system will shift its equilibrium position so as to counter the effect of the disturbance. Let's first look at concentration, and this involves either adding or the removal of a product. Here we have the initial equilibrium. We have equal amounts of reactants A and B, producing one product, the yellow box. If we add more of reactant in the blue box, we are altering the equilibrium. Therefore, the equilibrium will shift to the right to produce more of the product. As we can see, the yellow box is increased in size, which ultimately decreases the amount of reactant in the blue box. To change the pressure, we need to change the volume. So we can see here the initial volume, and when we increase the pressure, we are making the area of where the particles are smaller, and this produces a change in the equilibrium. Therefore, the equilibrium will shift in the direction of fewer moles. If we change the temperature of a system at equilibrium, the system will react as if we added a reactant to an endothermic reaction or a product to an exothermic reaction. If we have an endothermic reaction, if we increase the temperature, the reaction will shift to the right in the forward direction, because of the endothermic nature means that the overall temperature will decrease. If we decrease the temperature in an endothermic reaction, the equilibrium position will shift to the left because it is exothermic in the reverse direction, meaning that the temperature of the system will increase to go back to the original starting point. If we have an exothermic reaction and we try to decrease the temperature, the equilibrium will shift to the right because the forward reaction is exothermic, so it will ultimately increase the temperature, leading us back to our starting state. If we have an increase in temperature, the reaction will shift to the left because the reverse reaction is endothermic, therefore the temperature will be lowered. Let's now look at some specific examples. We have this reaction between N2O4 going to 2 moles nitrogen dioxide. The forward reaction is endothermic, which means that the delta H is positive. So if we increase the temperature of this closed system, let's say by placing it into a water bath, the equilibrium will shift to the right in favor of the products, so in favor of the nitrogen dioxide. And this is because the forward reaction is endothermic, which means that it will reduce the temperature, trying to go back down to the original conditions. If we try to decrease the temperature for this reaction, the equilibrium will shift to the left because the backward reaction is exothermic, which means that this will lead to an increase in the temperature back to the original state. We can also consider the same example in terms of the changes in the pressure. So the pressure of a gas will depend on the number of molecules in the container. If we increase the pressure for this reaction, the direction of the equilibrium will shift to the left, so for the reactants, because there is only 1 mole of the reactant, but there are 2 moles of nitrogen dioxide. So if we shift the equilibrium position to the left, this means that we are reducing the number of moles, therefore we are opposing the increase in the pressure. If for the same reaction we decided to decrease the pressure, the equilibrium will shift to the right, so to the products, because there are 2 moles of nitrogen dioxide here, which would lead to, again, to an increase in pressure and a return to the original. In this reaction we have PCl5 gaseous going to PCl3 gaseous and chlorine gas. If we lower the concentration of the reactant, the system will reverse the reaction to make more of it. In this case, if we increase, let's say, the concentration of chlorine gas, the equilibrium will shift to the left to produce more PCl5. Let's look at some questions. In the first question, we asked to look at this equation here. And we asked, in which direction will the equilibrium shift when A, N2O4 is added? The system will adjust to decrease the concentration of the added N2O4, so the equilibrium will shift to the right in the direction of the product. For B, what will happen to the equilibrium if NO2 is removed? And NO2 is the product. The system will adjust to the removal of NO2 by shifting to the side that produces more NO2. Therefore, it will shift to the left, so we will have an increase in the reactant. And C, the pressure is increased by addition of nitrogen. If we add nitrogen, we are increasing the total pressure of the system. But because nitrogen is not involved in the reaction, the partial pressures of both nitrogen dioxide and N2O4 will be unchanged, so there will be no shift in the position of the equilibrium. D, so what will happen to the equilibrium if the volume is increased? If we increase the volume of the system, the shift will be in the direction that occupies a larger volume, meaning we have more gas molecules, therefore the equilibrium will shift to the right because there are 2 moles here and only 1 mole here. Finally, we are asked to consider what will happen to the equilibrium if we decrease the temperature. We are told here that the forward reaction is endothermic. Therefore, if the temperature is decreased, the equilibrium will shift to the left because the reverse will be an exothermic reaction. And this would allow the system temperature to increase back to its starting point. We are asked to look at this reaction where PCl5 is converted into PCl3 and chlorine gas. In which direction will the equilibrium shift when chlorine gas is removed? In this case, the equilibrium will shift to the right. Since we are removing chlorine gas, if the equilibrium shifts to the right, it means we are trying to increase the amount of chlorine gas, thereby going in the opposite direction of the change. B, what will happen to the equilibrium when the temperature is decreased? The forward reaction is endothermic. Therefore, the position of the equilibrium will shift to the left to try and increase the temperature. What will happen to the equilibrium if the volume of the reaction system is increased. If we're increasing the volume, the equilibrium will shift to the right in favor of the production of PCl3 and chlorine gas. And finally, what will happen to the equilibrium if PCl3 is added? PCl3 is the product, therefore the equilibrium will shift to the left to try and reduce the amount of PCl3.